Hi everyone, and welcome to the webinar today. Here is Rosaria, and I'm Marit, and we are data scientists at Knime. In the next half an hour, Rosaria will talk about the data science cycle, and I'm curious to know what she will tell us. If you have any questions, feel free to write them in the chat. I will collect them at the end, and she will then answer them. Have fun, and see you later.
Great, thank you, Marit. Okay, so let's start now. Okay, so welcome everybody to this Practice in Data Science webinar. This is a webinar that I wanted to run because every time that I start a new data science project, I get always the same question. So I've decided to collect the answers and to make a webinar about it. So every data science project starts with a relatively standard process. So the general development of a data science project follows a standard process. This is summarized in the CRISP-DM project. CRISP-DM means cross-industry standard process for data mining. You can see this is taken from Wikipedia, but you can see here all the steps involved in a CRISP-DM process. So here, first of all, we start with the business understanding. So that's the business case. We try to understand what the goal of the business case is. After that, there is a data exploration phase where we try to understand the data we are dealing with. And then finally, when we are happy with the kind of data, with the understanding that we have of the data set and of the business case, then we can move to the data preparation. And if the project requires a prediction, we can move to the training of the machine learning model. Another phase is the evaluation of the model. And the evaluation of the model measures the quality of the model. And when we are happy with the evaluation, with the quality of the model, we can move to the deployment phase. So we release our model and our application into the wild. If we are not happy with the quality of the model, we are going to start again with one of the previous phases. Okay, so let's continue. This is the how the CRISP-DM process is going to be translated into a Knime workflow. You can see here the same steps that we have seen in the CRISP-DM process. So you have here the data access, you have here the data preparation. Then if the project requires a machine learning model, we train the model here. And then the model is applied, and then finally the model is evaluated. So all the phases of the CRISP-DM process are actually easily translated into a Knime workflow. Okay, so let's in this part there should be also an optimization phase. It's not reported in this particular workflow, but the optimization phase can be easily inserted in this workflow as well. Okay, so everything seems standard. In a perfect condition, in a perfect world, the CRISP-DM process is going to be, everything is going to work fine with the CRISP-DM process. The data set is perfect for our model. Everything works fine. So the question now is, how standard is the standard process? Already starting with data preparation, we are usually dealing with data types that are not that standard anymore. It used to be that you have numbers and you have nominal values, and then you're supposed to feed these numbers and nominal values into the model. But now, with the larger amount of data that is collected every day, new kinds of data have started showing up, for example, text or images or other kind of data that are not the standard kind of data types. You might deal with strange distributions of the data. For example, sometimes you end up in problems where you have no examples for one of the classes. you might need to run transformations that are model dependent. So based on the model that you have chosen, you might want to run a special transformation. Also, the machine learning model. Do we need to train a machine learning model? Yes, no. If it depends on the problem, which model do we choose for which problem? If everything goes well and we reach the phase of deployment, there are two main problems with deployment. How do we display our results, and the scalability of the whole project, of the whole application once it's in the real world. Okay, so, but the conclusion is that the standard mining process is not very standard at all. When I start a new data science project, I often get the data engineers, they ask me this question if they have to actually train a machine learning model. They feel overwhelmed with the number of machine learning models around, and they wonder if the machine learning model is a desperate requirement for the project. Of course, it depends on the project, but there are many projects that don't require the training of a machine learning model. We say that a picture is better than 1,000 words, then of course, if that's the case for this particular project, a dashboard is enough. Then you show the results via a dashboard to your manager and everybody is happy, right? In this case, I aggregate the data of the New York City taxi data set, and then I show the different distribution of the taxi pickups via different plots. There are projects where you only want to describe better your current data. For example, if you have a customer description problem, then usually the customers are described in three ways. One is the revenues, how much money they generate for the company. One is the loyalty, how long they have been together with the customers of the company. And one is the behavior. So, for example, the buying behavior that they show. All these particular measures that describe our customers, they don't require any machine learning model, but just an aggregation or some kind of mathematical operation based on the data, on the raw data for the customers. Another kind of project where no machine learning is required is the measurement of the user behavior, for example, in energy consumption. In this case, often we want to distinguish the people who use energy during the day from the people who use energy, for example, only in the evening or, for example, during the night. So in this case, again, we aggregate the data based on time on times during the 24 hours, and based on that, we define the behavior of the user. Another classic example that only relies on the calculation and aggregations of the raw data is the clickstream analysis. Here we want to distinguish, we want to characterize the users, for example, based on how long they spend in front of a web page, or based on how many clicks they take before they make the final purchase. So even in this case, it's a lot of aggregation of the number of the clicks or of the time that they spend in front of a page. And then finally, sometimes some projects are only about aggregating data in a data warehouse. So in this case, you have the data from different data sources. You want to blend them together. Then the raw data all blended together are written, for example, in a database. After some kind of transformation, for example, an aggregation, you build your data warehouse. And then the data from the data warehouse are again transformed and presented to the final business unit, either in a dashboard or in an Excel file, or however you want to present it. That's the final result. This whole application requires only ETL transformation. ETL is for extract, transform, and load. So it's purely data manipulation operation. So the answer is not, you don't need to train a machine learning model for all your data science projects. Some of them don't need that. If you are working on a data science project that requires a classification or a prediction, then you can't avoid to use a machine learning model. So the problem, once you have your business case, is if the problem becomes if you want to run a classification or if you want to run a numerical prediction. The algorithms used for classification or for numerical predictions are different, right? So in this case, for example, I have a problem in hair color classification. So the classes are red, blonde, brown, and black. And based on some measurements made on the hair, I want to classify the kind of hair I'm dealing with. In this other example on the right, I have the energy usage, and I have a time series that tells me how much energy is used every hour. I have the measurement for now, and I have the measurement for the previous some days, right? So given the previous, let's say 20 hours, I want to predict how much energy is going to be used on Wednesday at 12 o'clock, something like that. So this becomes a number prediction. Dealing with classifications, those are the algorithms that can be used for classification. For example, you can start from a decision tree, which is the basic, but then you can move to the evolution of the decision tree and use, for example, the random forest or some gradient boosted tree to implement the same classification problem. So there are a number of those. I reported only a few here. If you are dealing with numerical problems, then there is another set of algorithms mainly based on regression, and then you can use, for example, the basic is the linear regression, move to a polynomial regression, and then start with the regression trees. There is not a clear division between numerical prediction and classification. For example, sorry, no, I forgot. So, and then there are the neural networks. Depending on the architecture of the neural network, you can define you can solve a numerical prediction problem, or you can solve a classification problem. Okay, so the difference between a numerical prediction problem and a classification problem is not so defined, right? For example, you can move from a numerical prediction problem into a classification problem, for example, via binning. A classic one is, I have my washing machine and I want to predict the price of my washing machine in the next 2 weeks. And that's a hard problem because I have to predict an exact number, which is the price of my washing machine in 2 weeks. However, I can simplify the problem and I can say that I want to know if in 2 weeks the price of my washing machine is going to go up or down or stay the same. Then I have reduced my numerical prediction problem to a classification problem with only 3 classes, which hopefully is easier to solve. The opposite is also true. So if I have a classification problem and I discretize the classes, I can always move into a numerical prediction problem, even though this one might not have clear advantages. When we talk about numerical prediction, I often get the question, but then do we have to use time series analysis? Okay, so a numerical prediction and a time series analysis, they might share similar algorithms, but of course the difference is in time. In a numerical prediction problem, I have a target variable y, which depends on the target on the input variable x1, x2, xn. They are numerical, but there is no time involved. So y depends on x1, x2, xn at any time t. So there is no time involved, right? Usually this is, for example, solved by a linear regression. This is an example. But so this is the whole formulation of the problem. In a time series analysis, I have that the target variable becomes the value of my time series at time t, and the input variables are the past values of my time series at time t minus 1 and back until t minus n, whatever n is, right? So the difference between this problem and this problem is time, that I'm feeding my model with a vector of past values of the time series. And in this case, the order, especially for some algorithms, the order of presentation of the input vectors during training, it's important because some algorithms, remember, can extract information from the order of presentation in time of the input vectors. So if on one side, a numerical prediction can be solved with all the methods that we have seen before, here I placed only the linear regression, but you can use also a regression tree or some other algorithms that can perform numerical prediction. The time series analysis requires the past in the input vector. So the input vector in a time series analysis has to contain the current value of the time series at time t, and also the past values of the time series in the same input vector. How do I get this input vector to feed my algorithm? I use this leg column node. The leg column node takes the time series column, copies it, and then shifts it down a number n of steps. And this shifting down a number n of steps allows me to build the vector of past values with which I'm going to feed my algorithm. So the difference between the linear regression here is that I can apply just the linear regression, while here, for a time series analysis, I need to build the vector of past values using the leg column node. Another algorithm would be, for example, the ARIMA. The ARIMA is another algorithm for time series prediction. I usually don't advise to use it because it's a bit memory consuming and quite slow, but in the past was used a lot. And then, of course, neural networks, they are also heavily used in time series analysis. Knime has an integration with the deep learning, as a deep learning extension which integrates Keras into Knime. The advantage of having Keras in Knime is that this Keras integration uses the same graphical user interface that all Knime nodes share. It becomes much easier because then I don't need a lot of Python code to build and train my network. I just need these nodes and the configuration of these nodes to, for example, build, in this case, a neural network with 2 hidden layers. And then I need only the Keras network learner node to train my network. So it becomes much easier. As I said, some of the algorithms, they can learn from the order of presentation of the input vectors into the model. They can extract information from this evolution in time, so from this order of presentation. One of these algorithms is a neural network that contains an LSTM layer. LSTM units, long short-term memory units, are recurring units, and given these recurring features, they have the possibility to learn to memorize the past in the order of presentation of the examples in a training phase. So if you want to use the neural networks, I would like to advise you to experiment with the LSTM units. Another error that people can do when they try to run a time series analysis is that they mix the future and the past. Usually the past is reserved for training, the future is reserved for testing. And you have to make sure that the past doesn't trickle down into the future, otherwise, of course, the testing becomes much easier. You can do that by using in the partitioning node the option take from top. If you have your time series sorted in time in a descending order, take from top takes only the past values of the time series and of the time series with their vector of past values. So this is one of the options that you can use not to mix past and future when you are dividing between training set and test set. Okay. So next question is, do I need to use supervised algorithm or unsupervised algorithm? Of course, this depends on the business case that we want to solve, but it also depends on the data. Sometimes there is no choice. So if you want to use a supervised algorithm, you need to have a labeled training set. A labeled training set means that every example in the training set has a class attached to it, has a label attached to it, or a numerical value attached to it. More often than not, we have unlabeled training set. So we have a training set where no class is provided for any of the examples. So in the case of an unlabeled training set, you have no choice. You have to use unsupervised machine learning algorithms because otherwise the supervised machine learning algorithms don't work. So if you want to use if you have a labeled training set and you want to use supervised algorithms, those are some of the options, okay? And some of them we have seen before in the classification and in the numerical prediction problem. If you have an unlabeled training set and you have to use then an unsupervised algorithm, you can use a clustering algorithm or an association rule algorithm, depending on the business case. Clustering algorithms are based on distance, so they aggregate examples, they aggregate vectors based on distance. Association rules, they aggregate vectors based on the co-occurrence of on the statistics of the co-occurrence of examples. Even here, the division between supervised and unsupervised, the labeled training set and unlabeled training set is not so binary, it's not so clear. It used to be that you have a training set, somebody labels it, you have a labeled training set, you perform a supervised algorithm, you train a supervised algorithm, or you don't, and then you use some clustering, for example. Now, with more and more data that become available, it's unrealistic to think that all this data can be labeled in a training set, because it costs a lot of money to label data in a training set. So now some new procedures are coming out, and they are called semi-supervised procedure. And the idea is that you label a subset of the training set, something that is still manageable and it's not too expensive, and then you use some procedure to extend the manual label of the subset of the training set to all the other examples in the training set. So one of that, for example, is the active learning. Another problem is the distribution of the classes. If you are in a perfect world, then the classes are all evenly distributed. You have all of them are perfectly represented in your training set. You train your model, the model sees all the examples and learns that all the classes have follow some particular pattern. This is the real world, though, so these things usually do not happen. So what happens more often than not is that you have unevenly distributed classes. Sometimes you actually want to keep this knowledge about the a priori distribution of the classes, and you want your model to learn about that as well. So in this case, when you use the partitioning node, you should use the stratified sampling, and you should apply the stratified sampling to the values of, for example, the class column. The stratified sampling performs a random extraction of the examples from a data set, but the random extraction follows the a priori probability of the classes represented in the selected column. Sometimes, however, some classes are very infrequent. So let's suppose that you have one class which is represented only by 10% of the data in the training set, and one class which is represented by 90% of the data in the training set. If the algorithm, sometimes the algorithms, they become smart, and then they learn to assign always the class of the most represented class. So they always assign the label of the most represented class. If they do like that, they are correct at least 90%. They're correct 90% of the time. So it's not too bad, right, to have an accuracy of 90%. Of course, this could be okay, depends on the problem, but sometimes we want that the algorithm also learns to recognize the least frequent class. For example, in a disease recognition problem, maybe the disease doesn't happen that often. It affects only 10% of the population, but we want to have to make sure that the algorithm can recognize the disease occurrences, even though they're not so frequent. So in this case, we have to force the algorithm to learn about this 10% part of the population. We can do that in two ways. We can subsample the most frequently happening class. So we take the most numerous class and we reduce it to have more or less the same number of examples as the least frequent class. This is done with the equal size sampling node. This, of course, is possible only if you have a lot of data, because you are going to reduce the data of the most frequent class. If you don't have a lot of data, then another technique is to do the opposite, to artificially create new examples of the least represented class following the same statistical measures produced available in the least represented class. This is done with the SMOT algorithm. The SMOT algorithm applied with care because of course it has to create a lot of new data and it has to measure it has to produce a lot of statistical measures. So at the end it's a bit slow. But sometimes you have no choice because you don't have that many examples, and then the SMOT is the only choice that you have to have a balanced training set. And sometimes you have absolutely no examples for one of the classes. This is actually not a classification problem anymore, but it is an anomaly detection problem. So we are going to have all the examples in the training set belonging to one class, which we will call the normal class, just to I mean, it doesn't have to be normal, we decide to call it normal. And then we are going to have from time to time some anomalies that are not represented in the training set, but we want to recognize them nevertheless. So the only thing possible here is to train the algorithm, the model, only on normal data. So then how can we recognize anomalies if our algorithm has been trained only on normal data? Usually we use a distance concept. For example, if you perform a clustering on your training set, you're going to cluster all the shapes, all possible patterns in your normal data. If an anomaly comes around, for example, during deployment, and you measure the distance of the anomaly vector with the cluster, with the centers of the cluster, for example, then in this case, you're going to have a very high distance because the anomaly is going to be hopefully very different from the normal data. On the opposite, if the input vector belongs to the normal class, then the distance is not going to be that high. So defining a threshold on the distance between the current input vector and the center of the clusters is going to give you an idea if that's a candidate for an anomaly or not. Similarly, if you want to run a numerical prediction, you can feed, for example, an autoregressive model with only time series that have been generated by a system operating in normal conditions, and then at the end you calculate the distance between the time series that has been predicted and the original time series. And if the distance on an observation window is bigger than some threshold, then that becomes also a candidate for a system that is not working in normal conditions anymore. Another interesting approach to detect anomalies is the autoencoder. The autoencoder is a particular architecture of a feed-forward neural network. The particular architecture includes one input layer, one output layer, and a few hidden layers. Here there is only one, but can be more. And the input layers and the output layers, they have the same number of units. The network is trained to reproduce the input vector onto the output layer. It's trained only on the normal data in the training set. So the idea is that the network is going to learn to reproduce normal data on the output layer quite well, but then in the case that an anomaly vector is going to be presented at the input layer, the network is not going to perform such a good task to reproduce the anomaly on the output layer. So in this case, again, we calculate a distance between what is the output of the output layer and the original input vector. And again, if the distance is higher than some given threshold, that's probably a candidate for an anomaly. So this is how the anomaly detection is usually solved. Let's talk now about data types. We have said that so far we have dealt with data which were actually numbers or nominal values, right? So those were the structured data we have always dealt with. Recently, with the proliferation of data creation by, for example, social media and other data sources, we have dealt with, for example, text or images or, for example, networks, so exchanges of information between users, for example, in a social media. the whole idea of incorporating text, images, networks, or even molecular structures or some other non-traditional data, unstructured data, is to reduce this data from whatever they are now into numbers. To do that, that's a processing problem, a pre-processing problem. We need some special processing units, processing functions for these particular data types. So Knime has a text processing, an image processing, and then a network processing, and even a chemistry extension. I'm not going to talk about the chemistry extension because I don't know it. But the text processing, the image processing, and the network processing allow you to, for example, get the text, isolate the words, clean up the words that are not of interest, and then transform the sequence of words into a sequence of numbers. And then the same for the images, and then also for an exchange into a social media forum, for example, that can be transformed into a graph, into a network graph, and then a number of measures can be extracted from the network graph. So all these extensions that are available in Knime can be useful to transform your special data into numbers. And then once we have numbers, we know how to solve it, right? We have trained a lot of algorithms, a lot of models, and we know exactly what to do with numbers. Okay, let's go now into the deployment. Once our model is, we are happy with the performance of our model as a good quality, then we are ready to release it into the real world. All deployment workflows, they work the same. They read the data, they read the model, they apply the model to the data, and then somehow they have some results. So the whole deployment process has a few challenges, and especially I would like to talk about two challenges of the deployment process. The first one is how I present the data. Of course, this one depends on the business case, so on how we want to, the final results have to be used for this particular business case. So sometimes, for example, we want to transform our workflow, our deployment workflow into a REST API that can be called by external applications, right? Or even by external workflows. So you can build a full orchestrations around these REST API workflows. Sometime we might want just to visualize our results into a dashboard. On the web portal, you can visualize your results in a dashboard, and you can do more than that. You can also define little interaction points where you can allow the end user to customize the execution of the application. So the screenshots that I have here, they come from the automated machine learning application that we have presented in one of the webinars before. And here we decide the algorithms that we want to train. And then in the next step, we have a dashboard of the performance of the accuracy and the ROC curve area, the area under the curve for each of the machine learning models, and as well as the training speed. Okay, sometimes we just want to have a nice report, I don't know, some geographical map or something, some nice flashy reports to give to our boss. Knime has some integrations. We can do that with BERT, or we can do that with Tableau or with TIBCO Spotfire. So, and then sometimes we don't want to present our results at all. We just want to save the results, for example, in a database, and then we need just to perform a remote execution of our workflow, or even schedule to the execution of our workflow to happen at a regular time every some days or hours or whatever it is. So these are some of the options. The other problem with deployment is often scalability. Once we release the workflow into the real world from the, let's say, protected area, protected environment of our lab, we might need to be worried about some scalability issues. So one way to make our workflow more scalable is to, for example, export it into Spark. In this case, we can use the Spark integration, and we use these nodes, again, the same graphical user interface, which makes the interaction with Spark much easier. We can also use the feature from the Knime server with the parallel execution. This is an example, this workflow where I start a parallel loop, and then the load from the different chunks of the loop is distributed in the different parallel executors of the Knime server. And then finally, we can also use for if it's only an if it's only a purely data manipulation application, we can use the in-database processing and, for example, run it on a Hive platform or some other platform that allows for in-database processing. Okay, so we have reached the end of our webinar. Those were the questions that we have tried, I have tried to answer, and those are the questions that I usually get every time I start a new data science project. To conclude, I would like to invite you to the Knime Spring Summit. The Knime Spring Summit is going to start on Monday in Berlin at the Berlin Congress Center in Berlin. On Monday and Tuesday, we are going to have courses. So if you want to know more about Knime or something else, you can take one of our courses. But the heart of the summit is going to start on Wednesday and Thursday, where there are going to be sessions where we show case studies for real production-ready applications in data science. And then on Friday, we have some workshops. If you want to register, you can use this code and you get 20% discount on the ticket. And to thank you for having stayed with me until now, I always have a gift at the end, and you are going to get a free copy of the Practice in Data Science ebook from the Knime Press. So you can go to the Knime Press page, and then you can download the Practice in Data Science book for free using this code here, this promotion code here. However, don't do it now, because there is a second edition coming. At the moment, the book Practice in Data Science contains 10 case studies, and some of them use some of the tips and tricks that I've shown you in this webinar. However, next week, we are going to have the second edition for the book. We are going to premiere the second edition of the book at the Knime Summit. So if you wait until the end of next week, you can download the updated version of this book with 22 case studies. You can also come to the summit again, and then you can be present at the premiering of this new edition of the book. Okay, so I think I'm finished with my webinar. I think we can pass to the questions.
Okay, hello. Thank you, Rosaria. That was interesting. And thank you for your active participations, because we have a couple of questions that you can now answer. First question, if I'm completely new to data science, where do I start with Knime?
Okay, so to learn Knime, we have an e-learning course on our website. It's under learning and then e-learning course. So you can start from there. It's organized in sections, in chapters. So you can start from the basic at the beginning, how to install it, how to read a data set. And then, of course, it grows in complexity with, for example, how to perform a time series analysis. That's the latest addition that we have.
Okay, thank you. And then, is Knime suitable for big data?
Yes, so we have the big data extension, as I showed in deployment during when I talked about deployment. We have a big data extension. The big data extension, it's an integration with Spark and all the big data platforms. So you can use the nodes integrating with Spark, and then you can use the graphical user interface of the node, the dialog of the nodes, to control the Spark platform, to control the execution of your workflow on the Spark platform. Absolutely.
Okay. Then the next question is about data pre-processing. When do I know that I have pre-processed the data enough? And why do many models stuck? Because the data pre-processing was not enough.
So if you remember the CRISP DM cycle, there was this, so the whole cycle going around, and there was the data preparation, then the training of the model, then the evaluation of the model, and then the deployment. After the evaluation of the model, if the quality of the model was not good enough, we were starting again from one of the previous phases. Right. So there is no hard rule to say now, Zach, you're ready and you can start with the training of the model because the data have been prepared and it's okay. The quality is good enough. You try, you check if the model performs well enough, and if it doesn't perform well enough, then you can try some different data preparation. For example, you can have data that are too noisy or too many missing values or things like that. So these steps are kind of standard, but sometimes you need to go back and try again.
Okay, and you said about exporting data to a dashboard that you have pre-processed in Knime. Which interfaces exist there?
So I've shown you before that you have the the official nodes, the official integrations are with Tableau, TIBCO, and BERT. However, most of the reporting platforms, they accept, for example, CSV files, and then you can just export your data into a CSV file and then re-import it in your visualization tool of choice.
Okay, and then there is one question about the certification program.
Ooh.
Please explain it.
The certification program. Okay, so we are going to start certifying people. The first certification exam is going to take place at the summit next week on Friday. And we have two levels of certification, L1 and L2. L1 is the basic part, so where people are supposed to know enough about Knime, and then they are going to be certified about basic knowledge of Knime. The L2 is a bit more advanced, and people are going to be certified about an advanced usage of Knime. So there is going to be some questions, for example, about loops and control structures, and so more complex models rather than just basic operations in Knime. You can register. It's on our website in the summit web page, and then you can register for this certification. You can register for the L1 or the L2 or both. There is a fee to pay, but it's not that much. So,
okay. And then, what is a good way to share or collaborate using Knime?
So if it happens often that people work together in a lab on the same project, right? And then we go back and forth on the same workflow, and then I pass it to my colleagues, and then they do some improvement, and they bring it back to me, and then I say, the improvement is nice, but we need also this one. Then I put something else, and so on. So usually we use the Knime server to do that because it's easier. You just mount the Knime server, you have it available on your Knime Explorer here on the top left corner. So you open it, and then you just drag and drop files around or deploy to the server and things like that. So for sharing, it's much easier. You can also export file workflows using the export workflow and import workflow function in the Knime Analytics platform, but of course it's a bit more complicated. If you do it once in a while, maybe it works, but if you have to constantly exchange information, probably the Knime server is a bit more comfortable to use.
Okay, I think this was to the dashboards again. Will there be support for Power BI in the future?
Okay.
Do you know?
What am I supposed to say? That it's a promise. Let's say that there is the will.
Okay.
I'm not going to say much more than that.
Okay. Then you mentioned active learning. Where can the people find more about it?
So the active learning, we are going to have a workflow on the example server soon. I think the only example that we had was on the TeacherBot white paper. So you can go into the section white paper again on the website, learning white papers, and the TeacherBot had an example for the active learning. We are going to have something more dedicated to active learning soon, though. Absolutely. If you, there was my email address at the beginning of this presentation. You can send me an email if you want more information, and I can give you the exact link where you can find all these white papers and the next ones to come.
Okay, thank you for these questions. Very interesting questions. For the new ones, welcome on board. And for the older ones, thank you for your participation.
Thank you, and I hope I'll see you at the next webinar.
See you.